Hello. This unit is going to be on variational autoencoders. Um, this is a very prominent modeling technique these days in deep learning. It goes back to something called variational Bayes. So I'm first going to take a sort of variational Bayes view of variational autoencoders, and then we'll shift to a more modern deep learning view. So variational autoencoders are fundamentally about latent variables. So a primary example of this is when a child learns the phonemes of its language. It's given just sounds, speech sounds, and it learns to interpret those speech sounds in terms of some kind of phonetic symbolic representation, and then those phonemes get put together into words. But the point here is that the data the child is learning from does not explicitly say what the phoneme sequence is. So we're given data like the sound wave, and we're trying to discover latent structure. And I'm going to use Y for the data that we're given, like the raw sound wave input, and Z for the latent structure, like the phonemes. This phenomenon of recovering latent structure happens in many domains. So the latent structure might be parse trees. We learn how to parse sentences, but we're never given labeled phrase structure diagrams. We learn how to segment images into the objects that are in the image. We're never given that segmentation. Similar things happen with our understanding of depth or the class names, the categories, dogs. So here we're interested in a very abstract general setting where we've got some probability distribution over some input space, some data space Y, and we're trying to interpret that data in terms of latent structure. And we're doing that only from the observations of Y, not latent, not labeled data. And so I'm going to start taking this Bayesian approach. We often think of the latent structure Z as the causal source of the observation Y. So Z might be a physical scene that's causing the image, or Z might be a word sequence that's causing the speech sound. And that leads to a certain kind of model structure. The model structure is assuming a probability distribution over the causal source, like the scenes. And what we're getting is evidence about the scene when we take a picture. The picture is evidence about what the 3D reality is. So this is our model structure. I'm going to define the probability defined by the model. So the model has two pieces. It has a prior on the latent structure and a conditional probability of our observation given the latent structure. So this is sort of a model structure that is commonly used, especially in Bayesian circles. This model structure, which is really a joint distribution on the latent and the observed, defines a probability on the observed data. So these two parameters define a probability on Y, on the observation, which is a sum over all possible latent values of the joint probability. This is just the standard definition of a marginal, how you compute a marginal distribution over a joint distribution. And then there is a probability, you want to reverse this process if you really believe that this is the truth. So this is something that Bayesians do. They tend to make a model and then believe that the model is actually true. That's not often done in deep learning circles, but we need to consider that place to stand. We're going to assume the model is really true. If the model is really true, then if we get an observation, what we want to compute is the probability distribution over the causal source Z given the observation. But our model goes the other way, right? It's not, our model is able to infer the observation from the latent data, but it's not able to to infer the latent data from the model. Not when it's phrased this way. Even if these are very simple models, this can be very hard. So this is just the standard definition. It's the joint probability divided by the probability of Y, where the probability of Y is defined by this thing. So this, if Z is a structured object like a scene or a word sequence, even if these models are very simple and you can easily compute and sample from these models, this inverse problem of understanding the latent structure, the scene from the image, is computationally intractable in general. If this is an exponentially large space of Z, this sum becomes exponentially large. Okay, so now we're going to start working on the formal mathematics. So I'm going to assume that the model has these two parts, that our model, which we're taking to be true, is simple. So each one of these parts is both computable, meaning if you give me a Z, I can compute its probability, and it's sampleable, meaning I can draw random samples from this distribution. And I'm going to assume both of these pieces of the model are simple in this way. We can compute their value and we can sample from them. So these assumptions include autoregressive models, like language models that generate one thing at a time. You can compute the probability of a sentence and you can sample a sentence. It's also true of Gaussian distributions. You can compute the density of a point in the Gaussian and you can draw a random value from the Gaussian. So the question is, can we find an efficient way of computing the probability of a given evidence? So if we're going to train a model, now I'm going to back off and say, well, ultimately we're going to be interested in training our model and this Bayesian model. If we're going to train a model, we ultimately would like to train it by log loss, right? This is the standard log loss, cross entropy loss way of training a model. We can observe, we can make observations, and we want a model that minimizes the cross entropy between the population distribution and the model distribution. Now, a naive way to do this, and the Bayesians might not be interested in this optimization problem. They're more interested in just, what's the probability of Y given Z? So they're very interested in being able to manipulate this distribution. But if I could compute this value somehow, then I could do this optimization. Yeah, so I've said that. So that this inverse probability and this model probability of Y is typically intractable. And that's because this sum is over an exponential set. Now, one way we might try to do this is we could just sample Z. I've assumed this is sampleable. I could just sample Z and compute this probability of Y because, I'm sorry, that should be Y given Z. This should be Y given Z. I could sample Z and compute Y given Z, and that process, the expectation of that process would be the probability of Y, because that's exactly this expression. But there's two issues. One is this is an exponentially large set. And the other issue is if I just sample from this, I'm very unlikely to hit the values of Z that dominate this sum. The values of Z that dominate this sum are really the values of Z that are maximum under the conditional probability of Z given Y. So we could adjust this with a classical method called importance sampling. So we take this expression, and instead of sampling Z from this distribution, we're going to sample Z from the posterior on Z given Y. So this is much more likely to hit something that's maximizing this probability. So, but if I sample from this, then I need to adjust the probability. This is the standard importance sampling trick. I adjust this probability such that the expectation under this sampling is actually P of Y. It's this importance sampling, where I'm sampling from this, is equivalent to sampling from P of X, because this expression, the probability of Z given Y, cancels. So that's importance sampling, and that would be very useful here. But unfortunately, this probability of Z given Y is also intractable. We can't sample from that because we can't really compute that. So in variational Bayes, now I want to think Bayesian, this is what I'm really interested in computing, right? I get a picture and I want the scene. I want to invert the causal model, go backward from Z causing Y to what Z given Y, what Z is likely. So variational Bayes is going to sidestep this problem by introducing a third component of the model. We not only have a prior on Z and a probability of Y given Z, but we have a model that's estimating the probability of Z given Y. And intuitively, that's what we would like. We would like to be able to sample from this posterior, and we're going to make this model that posterior on Z. So here's the ELBO, the evidence lower bound. So well, we're going to sample from the model probability distribution on Z, and then we're going to compute this expression. But let me digest this a little bit. This is what we're interested in, right? If we're going to do our log loss optimization, we have to be able to compute this. And this appears here. And all I've done is I've taken this, sorry, it appears here. And all I've done is I've taken this, which is the thing I'm interested in, and multiplied and divided by the same thing. So this is just the log of this probability. And Z does not appear here. So this is sort of becomes trivially true. This first step is a little mysterious. You just introduce a sampling thing that this doesn't depend on, and then you multiply and divide by this. But then what I can do is I can take this piece right here and replace it by the model. So now I've replaced this by the model of Z given Y. But all I've really done is multiplied and divided by that model, and then taken this over this out as a separate term. Now, this expression is now, if I take this expectation and put it over here, it's now a KL divergence. And this KL divergence is always positive. Is never negative. KL divergence is never negative. And that implies that if I drop the KL divergence term, what's here must be smaller than this, right? So then I get this expression. This expression is now a lower bound on the log probability of the evidence. So remember, Y is viewed as evidence about the underlying Z. So this is the evidence lower bound, the ELBO. And this is optimized. This becomes exactly equal if this KL divergence is zero. If this KL divergence is zero, this becomes exactly equal. And this KL divergence is zero when this model is exactly the posterior distribution that we're looking for. So if I optimize this with respect to psi, I get a model of the posterior inference. So this optimization is going to give me a model of the posterior inference. That's the very Bayesian view of this. So this is what we just derived. This is the ELBO. I can take this numerator in the ELBO, and I can break it the other way, right? I can break it up into the probability of Z and the probability of Y given Z. This is the probability of Z and Y under the model. So the probability of Z and Y under the model, I break up this way, and this is the typical way of writing the ELBO. Then I rearrange these three factors by pulling this one out. And I also negate it, because this is the thing I'm going to optimize in my cross entropy loss. So when I negate it, the sign flips. So I've negated this, and I've pulled this term out. And this is the standard way of writing the ELBO in deep learning, right? So this is the thing I want to minimize. And if this was correct, this inequality, if this was exactly the posterior, this inequality would be equality. So that's the ELBO, and this is the variational autoencoder. Now we have three parts, right? We have three models. We've got a prior on Z. This is our prior on Z. We've got a model giving us a model of the probability of Z given Y. And we've got and our Bayesian model is these two parts, right? It's the prior on Z, and it's the posterior of Y, or the probability of the evidence Y given Z. Now, a variational autoencoder is called an autoencoder because we can think of two pieces of this model as coding and decoding. So this is viewed as a decoder. It's taking Y and it's coding it into some Z. So this is the, did I say decoder? Encoder. This is the encoder and this is the decoder. So we call P of Z the prior. We call P of Z given Y the encoder. And we call P of Y given Z the decoder. And this term here, note, it's important to note that this term here is a KL divergence because we're sampling from this distribution and taking the log of this probability. And this is called the rate term. There's a communication interpretation of this where this is the amount of information, the mutual information, or a model of the mutual information that between Y and Z. We can ignore that, but it is called the rate term. So we've got a prior, an encoder, and a decoder. And I'll try to use those words, prior, encoder, and decoder, rather than these parameter names, phi, theta, and psi. But now so this is our model now. This is our optimization problem. We're going to try to minimize over the three pieces now, the encoder, the prior, the encoder, and the decoder. We're going to try to optimize over those three pieces this optimization, this objective function, which is basically a negative ELBO. Now there's a problem with this objective function, and this is just a technical problem and a technical trick. So I'm going to show you the technical problem and the technical trick, and then I'm going to ignore this in the rest of the slides. We want to optimize this over this encoder, right? But we're drawing samples from the encoder. And as we change the encoder, this distribution is going to change. So that's not what we're used to. We're used to drawing from the population, which is a fixed distribution, and training our model, our minus log probability in the cross entropy. Here, we're optimizing something that is changing the distribution of the data we're drawing from. And there's a trick called the Re Parameterization Trick for getting around this. What we do is we define a deterministic encoder that takes a random noise variable as an argument. Often this is taken to be Gaussian noise, but you can think of this as a big sequence of numbers between 0 and 1, sort of probability draws. It's random noise. And what we're going to do is define a deterministic generator of Z that's taking random noise such that if I consider the conditional onto Z over drawing the random noise, I get this distribution, right? So I can think of a probability distribution on Z given Y as being constructed by generating some random noise and then computing Z from Y plus the noise. So Z is not determined by Y, Z is determined by Y and the noise, and it becomes a distribution. And then when I do that, my optimization problem looks like this, right? I'm holding the sampling distribution fixed at drawing Y from the population and epsilon from noise of something I can compute now. This is deterministic, and I can take gradient descent on psi. So it's a trick. But I'm going to ignore it in the future and just write this, just with the understanding that there's this trick to do the optimization even through this position. Okay, this is a slide for people who've seen expectation maximization in some other class. If you haven't seen this, you're probably pretty safe ignoring this slide. Expectation maximization is probably the most conceptually difficult thing in a typical introductory machine learning class. Expectation maximization is also about learning models with latent variables where the latent variables are not observed. And in expectation maximization, there's these two steps. There's an expectation step and a maximization step. It's the expectation maximization algorithm. And you just repeat those two steps. And the observation here is that the two steps of expectation maximization correspond exactly to alternating optimization of the VAE, of the ELBO objective function. So remember, the ELBO objective function has these three parts, which you can really think of as two parts. There's the Bayesian model, which is the prior on Z and the probability of the evidence given Z. That's the Bayesian model. And then there's this model of the inverse inference, sort of the inverse inference model, which is the encoder, the probability of z given y. And we can optimize these in an alternating way, right? We optimize, what we do is we hold the encoder fixed and optimize the Bayesian model. Or that's the M step. Or we can hold the model fixed and optimize the encoder for a fixed model. And the point is that EM is exactly alternating optimization of those two pieces. So EM is really a very special case of the variational autoencoder. The variational autoencoder is a generalization of EM. Dramatically weakens the requirements. You can use variational autoencoders in cases where EM cannot be computed. Those two steps are intractable. Those two steps are intractable in general. They're only true for very special models. Okay, this is something that I've only recently come to really appreciate, and this is encoder autonomy. So this is the VAE. I've written that in the first line here. And I'm going to consider the model part of this, right? So Bayesian, would tend to think that the models are real, and they're interested in optimization or inferring the latent structure given an observation under some model that they take to be given or real. Here we're optimizing the model. So if we take, I want to consider this optimization function where I hold the encoder fixed. That's a little strange, right? Because normally we think of the encoder, the Bayesian would think of the encoder as approximating the inverse inference, but I'm not going to do that. I'm going to take the encoder to just be any fixed encoder. If I take any fixed encoder, the only term in this equation that depends on phi is this last term. And that means if I optimize, sorry, this is the decoder. The only term that depends, this is the only term that depends on the decoder. And this is the only term that depends on the prior. So if I optimize the prior and I optimize the decoder holding this fixed, I get these two simple cross entropy objectives that are being optimized. So if I'm holding the encoder fixed, and if I look at the optimization on these are just cross entropies. And these are going to have optimum when the cross entropy matches the distribution of the data, where the distribution of the data is this. So that implies that the optimum value for the prior is exactly the value is exactly the marginal of this distribution. So if this is optimized perfectly, this distribution here, the prior that we get, will be the distribution of the data, that the sampling distribution that we've got, which is drawing the y from pop and z from our encoder. And the same thing happens for the decoder. The decoder is the optimum decoder for the model I'm generating from. And if these equations are true, then the population distribution on y is exactly this distribution, because both of these are optimal, right? This is computing the optimal distributions under the population on y and the encoder on z. So if I get the optimal model under that distribution and I marginalize it on y, I get the population. So what's the point? The point is that if I hold the encoder fixed and just train the model, the prior and the probability of the evidence given the prior, and I do that, and we have universality, I get the population distribution. And that's also going to be the minimum of the VAE objective function. The VAE objective function just becomes the entropy of y. So I'm calling that encoder autonomy, right? The encoder can be anything. and the other two pieces that we're optimizing simply model the encoder. And if they model the encoder and the population perfectly, the marginal on the population is recovered. Encoder autonomy. So the next unit is going to be on, or a future unit is going to be on vector quantized variational autoencoders. And vector quantized variational autoencoders use what I'm going to call two-pass optimization. And for a long time, I was confused about this two-pass optimization approach in vector quantized variational autoencoders, because it felt like, the ELBO is jointly optimizing all three pieces. And in this two-pass optimization, we're not going to do that. But this two-pass optimization, you can get a lot of insight into this from the realization of encoder autonomy. Okay, so what is two-pass optimization? So I'm going to fix the prior at something really simple and naive. Doesn't really matter. Fix the prior at something that is, basically trivial. And then we're just going to optimize the encoder and the decoder for the fixed prior. So in the VQ VAE, we just take the prior to be a uniform distribution over a set of symbols. Very simple. And all we're going to do is, for this very simple fixed prior, we're going to optimize the encoder and the decoder. Now, I'm saying I'm holding the prior to be very simple, but I want to optimize this decoder very aggressively. Okay, so now, after I've done that, I'm going to optimize the prior. Sorry, I'm ahead of myself a slide. So now we're holding the prior to be fixed and simple. Again, the only term that depends on the decoder is this term. So when we optimize the decoder aggressively, we get, if this was universally expressive, we're optimizing a cross entropy from this distribution into the decoder. And if this was done perfectly, then the decoder would be exactly the conditional probability under this distribution. Now, once we've done this, we train the prior aggressively, holding the encoder and the decoder fixed. So now we're training the prior aggressively. And so now, just like in the observation on encoder autonomy, we observe that both the prior and the decoder are optimized by simple cross-entropy losses in this two-pass phase. And if we've done it aggressively in each of the passes individually, we get a perfect model of the data, right? Because they both satisfy this cross-entropy objective relative to the given encoder. So the bottom line is that this two-pass approach, you can sort of think of this as alternating optimization of one piece of the model with another piece of the model, if done aggressively, produces an exact, in one pass, if done aggressively and under universal expressivity, produces an exact model of the data. And I think that's an important insight, and certainly relevant to what we're going to see in vector quantized variational autoencoders. So I'll stop there. Thanks.